In this part of the chapter, we will talk about the statistical properties of our estimators. Now, you want to remember that when we talk about statistical properties, these have nothing to do with a particular random sample that we are working with, but rather we are talking about the statistical properties of estimators when random sample is done repeatedly. So remember that we are talking about random sampling done repeatedly, and we are then thinking about these statistical properties. So we're going to be talking about the following three things in this part. The expected value of OLS estimators, the variance of OLS estimators, and the efficiency of OLS. And we'll talk about the Gauss-Markov theorem and the Gauss-Markov assumptions. So these might mirror a lot of the assumptions that you've seen before. So the first assumption is that we want linearity in parameters. So we can write out a population model with many x's now, many independent variables, and we're trying to explain the dependent variable y. Remember that we can allow for y and x to be nonlinear functions of each other. So you could have terms like x squared or x cubed or log of x in your regression, or log of y in your regression. Okay, so that way the model is very flexible. However, the parameters that we talk about, these beta naughts and beta ones through beta k, these are just linear functions of x and y. So the second assumption is this assumption of random sampling, and this we've studied in great detail in chapter 2. But basically, this assumption implies that the data are representative, that they basically are a representative sample from the population of interest. Okay, so each cross-sectional unit, for example, in your random sample should have an equal chance of appearing in your sample. Okay. The third assumption is going to be a little more involved because we have more x's. Or more independent variables now. In the simple linear regression case, we only had one x. So the assumption says that there should be no perfect collinearity. Now, I would split this into two things. So the first thing you want when we're thinking about this third assumption is that you want some variation in your x's. So variation in your explanatory variables. And the second thing you want is this assumption of no perfect collinearity in your x's. So we basically want to rule out any case where the x's are perfectly linearly related. So something like this. If you have a regression model which is something like this, right? You don't want to have some sort of a relationship like this that you find in your data, which is basically saying that x1 is perfectly correlated with x3. Okay, so we want to avoid any such situation. The problem, if you have a perfect collinearity or perfect correlation of any two variables in your sample, is that you're not going to find any unique OLS estimators. Okay, so remember what we're trying to do in linear regression. We want to find unique values of these estimates, OLS estimates, which is basically you're getting that from minimizing the sum of squared residuals. Okay, so sometimes, even though this problem doesn't arise very much, it can arise from a bad specification of a population model, or sometimes if you have a very small sample size, you can have some issues with that. So you always want to make sure that your n is much, much greater than the number of estimators that you have. Now, here's an example. So here, like I was telling you earlier, if you had some variable x1, let's say this is your x1, education, you shouldn't have a relationship that is saying that education is perfectly correlated with experience. So education's 2 times experience or education's 100 times experience, whatever that relationship might be, you don't want to have a relationship like this. Okay, so this is not going to work for us. Okay, so assumption MLR3 will be violated. Okay, so be careful about that. Now, there are many other examples where this might be violated. So one thing you want to avoid doing is that if you have some variable, let's say we were talking about CEO salaries, okay? And you want to say that CEO salaries, let's say the model says that CEO salaries depends on firm sales, okay? Makes sense, right? You don't want to incorporate firm sales in, let's say, dollars, and then introduce another variable which is measuring firm sales in millions of dollars. So you want to avoid something like this, right? This is just going to be saying that this variable x1 and x2 are perfectly correlated, right? Because this is just a unit change. So you do not want to include the same variable in an equation that is just measured in different units, okay? So you're not going to get any new information if you include another variable with different units, okay? So that's something you want to keep in mind. Another thing you want to be careful about is functional forms. Okay, so this is tricky. Sometimes you might want to have a model which is measuring elasticity, which is measured in a log-log model, right? So there's this coefficient beta 1, which is saying log of consumption is now equal to beta naught plus beta 1 log of income, right? So here you're measuring elasticity. And if you wanted to introduce some sort of a non-constant, if you wanted elasticity to be non-constant, one way you could think about is to introduce some sort of non-linearity. So you don't want to do something like this. So let's say we introduce log of income square here instead of in addition to log of income. Notice that log of income square can be written as 2 log of income. Okay, and so log of income here is just your x1. So here basically what we're saying is that x2 can be written as 2 times x1. And again, this is telling us that these two variables are perfectly correlated. So we're in trouble. Okay, so we again have violated this third assumption that we want to hold. Okay, so this is something you want to avoid. But if you wanted to introduce non-linearities, you could introduce something like this, where you're basically squaring log of income. Okay, so that entire thing, not just income, within logs. Okay, so this is fine, right? Because this is allowing for some sort of a nonlinear relationship to exist between this variable and this variable. You also want to avoid situations where you can pin down a variable based on another variable. Okay, so I think we've taken this example in chapter 2 where we're saying that the vote for candidate A is basically dependent on the campaign expenditures for candidate A. and campaign expenditures for candidate B. If there were only 2 candidates running, then total expenditure is basically expenditure A plus expenditure B. So you want to avoid something like this, introducing something like this. Okay, so one variable out of these 3 needs to be dropped because there's a perfectly linear relationship that holds between these 3 variables. So you want to introduce 2, but not all these 3. This is going to violate MLR3. Okay, so one nice thing is, yes, well, we want to keep this in mind when we're running our regression, but what happens is if we did run our regression with these mistakes, then the software, whether you're working in R or Stata or Python, these softwares might automatically drop these variables. Okay, but what I want you to do is to basically rely on yourselves to properly construct the model and interpret it. So you should never construct a model that's incorrect in the first place. Okay, so we can interpret this later. Okay, so what is allowed then? If we can introduce those 3, we can introduce some sort of nonlinear function for one of our x's. So we can basically say that the share that is spent on candidate A is given by this ratio, the expenditure on candidate A divided by total expenditure. So we can introduce something like this in our regression, and that's not going to be a problem because this is a nonlinear function of x1, which was expenditure A. Okay, so as long as it's nonlinear, it's okay, but if it's perfectly linear, that's a problem. Okay, so just to recap, we are not saying in our assumption MLR3, we are not saying that the explanatory variables have to be uncorrelated. They can be correlated. All of these explanatory variables can be correlated in the population or in the sample. The assumption also doesn't say that they cannot be highly correlated. Even that's allowed. The only thing we want to avoid is perfect correlation in the sample. Okay, so any correlation which is positive or negative one. Okay, so like I said before, these violations of the third assumption are rare unless there's a specification error in the model or there is some sort of a problem with the sample. But you want to avoid some mistakes like these. Okay, and finally, what we need for unbiasedness of our estimators is a fourth assumption as well, which is saying that we need to have the expected value of u given all our x's to be 0. So the 0 is a trivial assumption because of the intercept, and we've gone over this a lot. The real assumption is really that the expected value of x should not depend on the x's, right? So this should basically, the conditional mean of u should be equal to the unconditional mean of u. Okay, so the average value of the error should not change across the different slices of the population defined by the different x's. Okay, so in case u is correlated with any of the x's in your model, MLR4 is violated, and you're going to have, you basically do not have the estimator, which is unbiased.